The oldest known record of a variable star may not be from 1669. It may be from 1244 BC. The document is not a scientific text. It is an Egyptian calendar, Papyrus Cairo 86637, used to rate each day of the year as good, bad, or extremely bad. Scholars read it as lunar tracking and mythology for decades. Then a research team in Helsinki ran the numbers. They found a second signal inside the unlucky days, a period of 2.85 days. Not a lunar fraction, not a planetary orbit, something else entirely. The document is called the Cairo Calendar. The Egyptian Museum in Cairo acquired it from an antiquities dealer in 1943, and when scholars first examined it, they read it the way you would expect. A mythological almanac, a religious guide for daily decisions in ancient Egypt. Each of its 365 entries names a prognosis for the day, auspicious, inauspicious, or somewhere between. Do not conduct business today. This month is dangerous. Avoid travel in autumn. The calendar was, in all probability, used exactly the way a practical almanac might be used now. A guide for ordinary decisions in ordinary lives. No one who studied it in the early 20th century was thinking about astrophysics. The papyrus dates to approximately 1244 BC, the reign of Ramesses II. It covers the entire Egyptian year, one entry for each day. It is one of the best preserved documents of its kind, and for most of the 20th century, it was classified in exactly that way. A curious artifact, a religious calendar, useful for historians, unremarkable to astronomers, the kind of document that gets studied, published, translated, and then quietly shelved. That was the simple reading. For decades, it held. In 2013, a research team at the University of Helsinki examined the Cairo calendar differently. Lori Jetsu and Sebastian Porcedu ran a formal statistical analysis of every prognosis in the text. Not looking for mythology, not looking for hidden meaning, looking for periodicity, for any recurring mathematical pattern in the distribution of lucky and unlucky days. What they found first was expected. The calendar contained a strong 29.6-day signal. That is the synodic period of the moon, the time it takes to cycle from one new moon to the next. The moon governs tides, seasons, and human intuition. Lunar rhythm appearing in an ancient almanac surprised no one. The second signal was different. Embedded inside the same document, recurring with statistical precision across every section of the year, was a period of 2.85 days. Jetsu and Porcedu ran Rayleigh tests and Kuiper tests, formal statistical tools used to detect periodicity in noisy data. The signal held across both methods. It was not noise, and when they compared it against modern astronomical records, the match came back immediately. 2.867 days. That is the orbital period of Algol. Algol is a star in the constellation Perseus. From the Nile Delta, on any clear night, ancient Egyptians could see it hanging in the northern sky. It sits at 93 light-years from Earth, close enough to watch with no instrument, close enough to study across generations of careful observation. And it does something that almost no other bright star in the Egyptian sky does. It fades. The physics is not complicated, but the implication is. Algol is not one star. It is two stars in tight orbit, one passing in front of the other on a repeating schedule. When the dimmer star crosses the brighter one, the combined system loses roughly one full magnitude of apparent brightness. That is the difference between a star you notice easily and one that suddenly looks wrong, noticeably dimmer than the stars surrounding it. The primary eclipse lasts about 10 hours. Then it resets. Then it returns, every 2.867 days, without a telescope, without instruments, using nothing but dark skies, patient eyes, and consistent records kept across months and years. Any observer who watched Perseus carefully enough, for long enough, would eventually notice the pattern. The question is whether noticing it and recording it are the same thing. That should have closed the case. Statistical match. Physical mechanism. Ancient sky accessible to any observer. Simple. But the simplest answer here demands something unusual. For this match to be real, for the extremely bad prognoses in the Cairo calendar to genuinely align with Algol's dimming events, ancient Egyptian scribes would have had to track the brightness behavior of that star with enough consistency over long enough periods to encode its period into a document that modern statistical software can still detect 3,000 years later. Not because they wrote the number down, not because they labeled it a variable star, but because the pattern of bad days in their almanac carries a 2.87-day signal that is statistically distinct from the lunar cycle, and that signal survived. That is either coincidence or methodology, and Lori Jetsu understood exactly how difficult it was to claim the latter. He said it directly. I would have serious doubts if someone claimed, for example, that the Bible contains information about water on Mars. We claimed that ancient Egyptian religious texts contain astrophysical information about Algol. His point was not modesty, it was calibration. The claim was strong enough that he expected pushback from the scientific community, and he received it. Version 1 of this story is coincidence. The 2.85-day signal is an artifact. Human pattern recognition is extraordinarily powerful. It is one of our defining qualities. Any sufficiently complex data set, subjected to long enough analysis, will produce apparent periodicities. The lunar period dominates the calendar. Perhaps the smaller signal is a harmonic of that lunar rhythm. Perhaps the match with Algol is exactly the kind of false positive a careful scientist is trained to dismiss. That version has real merit. Some researchers held it for years. But the version has a problem. The dual match. Not one signal, but two independent signals, the lunar period and the Algol period, both recovered from the same text using the same statistical methods. Two mathematically separate cycles embedded in a single document. The probability of coincidence drops sharply when you are not explaining one match, but two. Jetsu's team published the initial finding in the Astrophysical Journal in 2013, then confirmed it in PLOS ONE in 2015 with additional testing. The paper was formally corrected once, then it was reconfirmed. It has stood in the peer-reviewed literature since. Version 2 is intention. The Cairo calendar calls the star Horus. The passages describing Horus in the text involve an eye that changes, an eye that dims, an eye that recovers. The mythological association between extremely bad days and Horus's changing eye, a symbol present in Egyptian religious tradition for centuries before this papyrus was written, aligns passage by passage with the night's Algol would have been at minimum brightness. The blinking eye of Horus is one of the most recognizable images in ancient Egyptian iconography. If that eye was also, in part, a record of what Egyptians observed in the sky over Perseus, the mythology becomes something other than mythology. It becomes data. But no Egyptian text ever states this explicitly. The methodology, whatever it was, did not survive. What survived is only the pattern it produced. Then the story shifts in a direction the ancient Egyptian scribes could not have anticipated. The star the Egyptians called Horus, described in the calendar's most hostile prognoses in passages Jetsu's team titled The Raging One, has since been studied by the Chandra X-ray Observatory. Not in visible light, in X-ray wavelengths. What Chandra found was not a quiet binary system ticking through eclipses. It found a system in active physical turmoil. The two stars in close orbit are transferring mass from one to the other. At X-ray energies, Algol flares. It emits intense radiation that no optical telescope can see. It is, in a directly and measurably physical sense, violent. The name was not dramatic license. Whatever Egyptians saw in that part of the sky, a star that dimmed on a 2.87-day cycle and seemed to carry a persistent hostile omen, they assigned to it a character that modern observatories later confirmed at frequencies the human eye cannot reach. The extremely bad prognosis was not superstition projected onto light. It may have been, in the most stripped-down scientific sense, an accurate label. The light that fell on Egyptian eyes in 1244 BC had left Algol approximately 93 years earlier. Whatever those two stars were experiencing in their close orbit, the mass transfer, the X-ray intensity, the precise dimming cycle, was not real-time to anyone watching. The information was already 93 years old when it arrived. The people at the Nile Delta under that sky had no access to the mechanism. They only had what the light told them, and what they recorded outlasted every dynasty that rose and fell beneath the same stars. The Egyptians were not alone. On the other side of the world, separated by ocean and nearly 2,000 years, a different civilization was doing something with Venus that scholars refused to call astronomy for more than 70 years. The Dresden Codex is a bark paper book. It measures roughly 20 centimeters tall and folds out to a little over 3.5 meters in length. It was made sometime in the 11th or 12th century, most likely in the Yucatan Peninsula, and it is one of the rarest objects on Earth. Of the hundreds of Maya books that once existed, only 4 have survived intact into the modern era. The Dresden Codex is held at the Saxon State Library in Germany. Among its contents are eclipse tables, ritual almanacs, and a sequence of pages that astronomers now consider one of the most precise astronomical records produced without modern instruments anywhere in the ancient world. Pages 46 through 50 contain the Venus tables. They document the synodic period of Venus, the time it takes Venus to return to the same position relative to Earth and the Sun, as 584 days. The actual synodic period is 583.92 days. The error is less than 1/10 of a day per cycle. Across the 104-year grand Venus cycle built into the tables, 65 Venus periods interlocked with the Maya calendar. That small error accumulates. The Maya scribes built a correction mechanism to account for this drift, a leap day structure, essentially, for a planet. They knew the number was slightly wrong, and they built the system to compensate. The correction was essential, and the drift was minimal. For more than a century, after the Codex was first studied by Western scholars, this precision was categorized as astrological rather than astronomical. The accuracy was called an impressive curiosity. In 2016, Gerardo Aldana of the University of California, Santa Barbara, published an analysis arguing that this framing was wrong. Aldana's reading of Dresden Codex page 24, the preface to the Venus tables, showed the table represented a genuine mathematical innovation developed at Chichen Itza in the 10th century. Not a ritual artifact, an independent astronomical discovery. A case of indigenous astronomical science being reclassified as primitive numerology for more than 70 years, because scholars assumed it could not be what it demonstrably was. That is where the assumption enters the case. The assumption that ancient records about the sky are mythology first and data second, if they are data at all. The assumption that precision without modern instruments is either coincidence or impossible. The Dresden Codex Venus tables were accurate. They were always known to be accurate. And for most of the 20th century, That accuracy was explained away rather than explained. Now, for the destroyed archive. In July 1562, in the town of Mani in the Yucatan Peninsula, a Franciscan friar named Diego de Landa ordered the burning of Maya manuscripts. The number destroyed is uncertain. Contemporary accounts suggest more than 24 codices, along with thousands of objects. De Landa later wrote that the books contained nothing but superstitions and falsehoods. What he burned, among other things, were astronomical records. The 4 Maya codices that survived, the Dresden, the Madrid, the Paris, and a fragment known as the Grolier or Mexico Codex, represent what remained after 1562, 4 books from what was almost certainly a much larger tradition. If one of 4 surviving books contains Venus tables accurate enough to remain scientifically useful in the 21st century, the question of what was in the ones that did not survive is not a small question. It is completely unanswerable. That is the point. The third confirmation came from the other side of the world much earlier, carved not on bark, but on clay. The Venus tablet of Amisaduqa is Enuma Anu Enlil tablet 63. It records naked-eye observations of Venus over a 21-year period, compiled during the reign of King Amisaduqa of Babylon around 1646 BC. The original is lost. The copy held at the British Museum, catalog number K160, dates to the Neo-Assyrian period, roughly 1,000 years later. Modern orbital mechanics has confirmed the accuracy of the Venus observations it contains. Historians and astronomers have used this tablet to help date Babylonian chronology to within a few decades. A copy of a record that is 4,000 years old is still scientifically useful. 3 civilizations, 3 separate writing systems, 3 different continents, 3 different mythological frameworks built around the sky, all producing records whose astronomical content modern science confirmed rather than dismissed once someone was willing to look carefully enough and willing to consider that the answer might be yes. The simplest record, in each case, was hiding the most precise measurement. None of these civilizations knew what the others were recording. None needed to. But there is a 4th version of this story, and it changes the shape of everything else. The peer-reviewed conclusion from Jetsu and Portsedu in 2015 was stated plainly. These 2 classical milestones in the history of natural sciences need to be shifted 3,000 years backwards in time to 1244 to 1163 BC. The milestones in question are the first recorded observation of a variable star, previously attributed to Geminiano Montanari in 1669, and the first measurement of a variable star's period, attributed to John Goodrick in 1783. If the Cairo Calendar finding stands, and it has survived peer review and formal correction and reconfirmation, both dates are wrong by approximately 3,000 years. This is published science. It is in the literature. The implication is not about Egypt specifically. It is about the line. The line that historians of science drew between ancient observation and modern science, between myth and measurement, between a calendar rating lucky days and an instrument measuring light. That line was drawn with confidence. It may have been drawn at the wrong place. Consider what it means that the line was drawn with this confidence. If you were the researcher at the University of Helsinki who ran the first Rayleigh test on the Cairo Calendar data, who loaded 3,200-year-old daily prognoses into a statistical program and waited for the output, the most unsettling result was not finding the Algol signal. It was understanding what its presence required. It required that someone, 32 centuries ago, had been systematic enough about watching the sky to leave a pattern that survived into modern analysis. Without knowing what a variable star was, without knowing what a binary system was, without knowing that the dimming they were recording was caused by one stellar body crossing another at 93 light-years away. The mechanism was invisible to them. The output was not. There is something else, something that did not come from Egypt, or the Maya, or Babylon. It came from NASA. On NASA's eclipse prediction pages, the agency acknowledges that values for Earth's rotational change, a quantity needed to accurately predict where on Earth past and future eclipses fall, can only be measured back to approximately 700 BC using one specific source. That source is ancient eclipse records, Babylonian clay tablets, Chinese astronomical annals, medieval European chronicles, records produced by scribes doing what scribes had always done, writing down what happened on a given night, are now the only way modern science can calibrate its own models of how the Earth's rotation has changed over 3,000 years. Stevenson, Morrison, and Hohenkirk published a refined analysis in the Proceedings of the Royal Society A in 2016, using hundreds of ancient records spanning more than 2,000 years. NASA cites their work. The ancient records that were once categorized as too imprecise to be scientifically useful are now too precise to be replaced. There is no substitute data. The past is not in a museum. It is in the calculation, which means the boundary between what ancient civilizations knew and what modern science knows is not fixed. It has been moving, not through discovery of lost technology or any dramatic revelation, through someone running a statistical test on a papyrus and someone checking an orbital mechanics calculation against a clay tablet, and someone realizing that the only way to know how Earth's rotation behaved in 700 BC is to find a person who was there and wrote it down. The Cairo Calendar is still being studied. New papers from Jetsu's group continue to appear. Algol is still being monitored. The Chandra X-ray Observatory has produced detailed profiles of the mass transfer occurring between the two stars that Egyptian scribes assigned to the eye of Horus. The star is still raging. The connection between a 3,200-year-old daily calendar and a modern X-ray observatory, between a prognosis of extremely bad, written in hieratic script, and a flux measurement recorded in erg per second, remains one of the most compressed links between ancient documentation and modern astrophysics in the scientific record. And still, the most important number is 4. 4 surviving Maya codices, not 30, not 20. 4. The Dresden Codex open to pages 46 through 50, Venus painted in red and black on bark paper, the synodic period accurate to within 1/10 of a day per cycle. That precision is what remained after 1562. Whatever the books that burned contained, longer observation records, more complete astronomical tables, deeper systematic traditions built up across generations, is now represented only by its absence. The number that looked impossible was not what the ancient world knew. It was only what it managed, against everything, to preserve.